Lesson 5.8, probability without counting. Today our main learning target is to find probabilities involving geometric regions. Let's go. Our warm-up review today is talking about finding an area of not your typical geometrical region. So why don't you go ahead and find the area of the gray region below. All right, if you need a little more time, go ahead and press pause. If you're ready to take a look at the finished product, let's go. How to find area. There really are two ways to do it. You can estimate by counting the squares that would fill the area, or we can be more exact by using a formula. We're going to actually use the second method. We're going to use a formula today as we're finding our areas. We don't have a formula for a ring, so to speak. Kind of the gray region here is a little bit of a ring or maybe a donut shape. So we must work with the area formulas that we do have. We can find the area of two separate circles. The gray area is a circle, an entire circle, including the brown part in the middle, minus, we would subtract or take out the brown part in the middle. So to find the area of a circle, we multiply pi times the radius squared. In this case, we are going to be multiplying pi times the 8-inch radius squared, which would be the entire circle, including both the gray outer ring and then also the brown inner circle, minus pi times 3 inches squared, which would just represent the inner circle that is not included in our gray area, so we do have to subtract that out. Following through here, I am not substituting in for pi yet. I'm going to leave that until the end. 8 inches squared would give us 64 pi inches squared, whereas the 3 inches squared would give us 9 pi inches squared. So if we subtract 64 pi inches squared minus 9 pi inches squared, this is really a lot of like terms, we have 55 pi inches squared. This represents an exact answer because we have not yet rounded anything. In order to find the rounded answer, we would in fact substitute 3.14 for pi, coming up with 172 7/10 square inches represents the gray region. Hopefully that warm-up dusted out some cobwebs on area formulas. You will be using them quite frequently today to find some different shaped regions, as well as just some basic regions, rectangles, squares, triangles, circles. So let's dive right in. Please recall that probability is the number of expected outcomes out of the total possible outcomes. So geometrically, what we're looking at is the measure of the desired or expected region out of the measure of the entire region. For this next example, we're talking about throwing a dart, randomly throwing a dart at this target over here. Consists of 3 concentric circles with radii of 20 centimeters, 40 centimeters, and 60 centimeters, as you can see here in the diagram. Assuming that the dart hits, again, that is assuming that the dart hits the board, so we know it hit the board. What is the exact probability that the dart lands inside the smaller? So we know that the desired region is the smallest circle here, so we're looking at the area of the smallest circle over the area of the entire target. The area of the smallest circle is, of course, a circle with a radius of 20, and the entire target, of course, is a circle with a radius of 60. So we're looking at 400 pi centimeters squared for the area of our smaller circle. Here you can see that I have done 20 centimeters squared to find the 400. Since it did ask for an exact probability, I'm not going to be substituting in for pi at this time. 3,600 pi centimeters squares comes from 60 times 60 with our pi. If we divide that out, it is 1/9 is our exact answer, or really, if we wanted to go percentage-wise, we do have to estimate here, we would come up with about 11%. Taking a look, this can also be done if we're talking about lengths. So here we have an example of lengths. When you look at this path below from the roof of your apartment building, you can only see the green portion of the path. If your friend is walking the entire path, when you get to the roof, what is the probability that you will see her at the moment that you reach the roof? So as we take a look here, remember probability is the measure of the desired region over the measure of the entire region. In this case, our desired region is this green portion right here. In order to find the measure of the green portion, we are going to have to consider that the entire length across the top, well, what we're reviewing as the top of this path is 5 miles, and we can see that this portion here represents 1 mile, so we know that this indicates 4 miles. We will also have to find the measure of the entire region, the entire path. Again, kind of moving some of our lengths around, we can see that a vertical distance here of 2 and another vertical distance here of 1 would indicate that this entire portion of the path does have a 3-mile length. So total, we have 4 miles out of 16 miles, which gives us about 1/4 or 25% chance that our friend is on the green part of the path and we would be able to see her from the roof of the building. And last but not least, we have another dart example, a very complex dart board here. Suppose you throw a dart randomly at the 2-foot by 4-foot board below. Assume the height of the triangle is approximately 1.7 feet. Assuming that you hit the board, so we know we hit the board, find the probability that your dart will land in the shaded region. You'll notice that the shaded region is not quite the entire triangle. There is a section of the triangle that we will have to take out. So our probability is, of course, equal to the measure of the desired region over the measure of the entire region. In this case, the entire region is a lot easier to figure out. The area of the shaded region. Again, the shaded region is almost an entire triangle, not quite. So we are, in fact, going to have to find the area of the triangle and subtract out the area of the circle that we see here. So we can see the area of a triangle using 1/2 base times height minus the area of the circle, which would be pi times 0.25 feet squared. You'll notice I did not use this number 0.5 feet here. That indicates the diameter, and the circle formula, it calls for the radius, not the diameter. The area of the entire region is, of course, the 2-foot by 4-foot board. So calculate each area. I'm going to calculate each area separately. 1.7 feet squared for the triangle. About, well, because I used an approximation for 3.14, about 19,625 feet for the circle and 8 feet for the entire board. I'm going to calculate the numerator so I can divide out for the percentage here. It looks like it's about 19% chance of hitting the shaded region. That's what we're taking a look at for today. We will see a few more examples in class next time before you begin practicing on your own. Have a good day.